All right. Thank you, everyone, for joining in. So today we have, it's our actual pleasure to have Professor Ricardo Vinuesa. So he's actually going to join the Department of Aerospace Engineering at the University of Michigan in fall of 25. He is currently an associate professor at the Department of Engineering Mechanics at KTH Royal Institute of Technology in Stockholm. He studied mechanical engineering at the Polytechnic University of Valencia at Spain, and he received his PhD in mechanical and aerospace engineering from the Illinois Institute of Technology in Chicago. His research combines numerical simulations and data-driven methods to understand, control, and predict complex wall-bounded turbulent flows, such as the boundary layers developing around wings and urban environments. Dr. Vinuesa has received, among others, an ERC Consolidator Grant, the TSFP Katsagi Award, the MST Emerging Leaders Award, the Goran Gustafson Award for Young Researchers, the IIT Outstanding Young Alumnus Award, the Ceres Young Researcher Award, and he is leading several large Horizon Europe projects. He is also a member of the Young Academy of Science of Spain. So please welcome Professor, and Professor, you can take it.
Thank you very much for the kind introduction, and also for the invitation to present today. I'm going to be talking about flow control in turbulence, and also about how we can use coherent structures and information about the flow to try to inform better control strategies. This is work funded by the ERC, the European Research Council, and this is developed in the context of the flow framework at KTH. So I would like to start by acknowledging my collaborators. So without them, this work would not be possible. And I'm also happy to acknowledge many other students and postdocs who have also been part of this work. So without them, this would not be really reaching this level. So very, very thankful to all of them. And also, I would like to talk a little bit about possibilities to control the flow. This is a typical airliner. I'm sure you have seen this slide before. What is interesting is that one can try to see for different contributions to the total drag. So you know that about 50% of the drag comes from friction. We can actually see what is the potential through technology opportunities of drag reduction. So in the friction drag, which is basically turbulent boundary layers, one can reduce about 15% of the drag in that portion. And the lift-dependent drag, which has to do with the wind tip vortices, there the potential is about 7%, more or less. So some kind of balance estimates tell us that it should be possible to reduce about 25% of the total drag in typical airliners, if not more, bringing in some new ideas and some new technology. So that's where we are heading, trying to be able to achieve as much as possible of this 25%. And I also wanted to show some of the stuff that we do within AI for Science. So we have a review paper now under review in Nature Computational Science, where we are trying to see how can AI be used for scientific discovery. And the take that we took in this review paper, Steve Branton is also part of it, and many other authors worldwide, is basically to classify the applications by how much we know about the governing equations. So on one extreme of the spectrum, towards the left, where we don't know so much, we will have, for example, brain research. So in that case, we don't know so much about the governing equations, and their machine learning can be used maybe to identify mechanisms which, through interpretable deep learning, can help us to discover equations or some ways of modeling fundamental mechanisms. And on the other way of the other end of the spectrum, the more we know, if we look at fluid mechanics, where we know the equations, we actually know very well the governing equations. We just lack details and understanding about the interactions between structures, between energy transfer mechanisms. Then it's useful to sometimes use, for example, example, reinforcement learning-based approaches for numerical experiments, such that we can create new flow ideas and try to understand how the energy behaves in those contexts. Or for instance, one can try to really look at very highly resolved data and see how dynamic events take place through data-driven methods and try to understand dynamically the physics of these events. So just some examples, but what I want to say is that generally it might be interesting when one looks at large organizations doing AI for science, which is going to be naturally multidisciplinary, to think in terms of not disciplines in silos, but rather look at applications together in terms of how much we know about the equations. If we know more or less, that's going to guide the type of machine learning AI applications that you want to use, and perhaps that can give you an idea of how we can work together, different disciplines in the same range of knowledge of the equations. So if you're interested, there is a preprint online, so feel free to have a look at it. The two main things I'm going to be discussing today is using explainable deep learning to understand turbulence, to try to understand coherent structures in turbulence. And second, I'm going to be using reinforcement learning to discover new control strategies and hopefully understand new ways to control and manipulate turbulence, hopefully reducing the drag. So in the first part, the question that we want to answer is what are the most important regions in the flow? And this is a question that has been analyzed in the past, for instance, by Encinar and Jimenez, who looked at this from the perspective of an interventional method. So they basically ran the DNS, the direct numerical simulation, they introduce perturbations, and then they look at which of those perturbations grow the most, right? And they have done this in homogeneous isotropic turbulence. They have recently extended the study to turbulent channels. And well, in that sense, you are actually changing the flow, right? Because you are rerunning the DNS. On the other hand, you can do something non-interventional, like Lozano Duran and Arranz, where they use information theory, causality-based methods, where one needs to have a time series. And you can do that through POD, for instance. And then on those time series, you remove the information of one time series to predict the other time series in such a way that you can see how that removal affects the future predictions. And this is non-interventional. So this is done in a post-processing step in a way such that you are not really affecting the original trajectory that you have of your flow. So this can be done in an interventional or in a non-interventional way. What we want to talk about here is an alternative approach, which is based on deep learning. And this is intrusive on the surrogate model. We can really create a surrogate model and make our changes there such that we are not affecting the original trajectory. And one advantage of this is that it can also be applied to environments with limited data like experiments. So we're going to start by analyzing a turbulent channel flow at a low Reynolds number. We're going to identify Reynolds stresses, so basically the Q events. These are regions, three-dimensional regions satisfying this equation, which means that the instantaneous product of the UV fluctuations needs to be larger than some threshold times the RMS of U times the RMS of V. Okay, so we basically want to look at volumes where the Reynolds shear stress is high, and that's the idea. And we want to classify this in terms of importance. So we want to look at if we build a predictive model, which can be a UNet, for example. So with a UNet, we can have the present state of the flow, which is given by the three-dimensional U, V, and W fluctuations. And then we can use this to integrate that in time and move it 5, 10 viscous times into the future. Then using Shapley additive explanations, the SHAP framework, which is a game theoretic method, we can basically remove structures from the input, repeat the predictions, and see how that's affecting my error. And in this way, we can get a pretty objective way to measure the importance of each of those elements. This is work led by Andrés Cremades in my group. It was published last year in Nature Communications. You can find all the data and all the code available online. So basically, if I go in a bit more detail, what I would do is that I have my present flow field, so the present instantaneous fluctuations. I use my UNet to predict the future state of the flow. I have my prediction. I can compare that with the ground truth, which is the DNS, and I calculate my error. And the errors are very low. I mean, we have now models that give us less than 1%. Then I go back to the input, I remove a structure, one of these Q events, and that removal is basically replacing by zero fluctuations, which is a non-informative field. I run my unit again, and I get a new predicted field, which I can compare with my ground truth, and the error will change. So naturally, some structures will affect that error more than others. And in this way, we can create what is called a ranking of importance. Each of the structures will have an importance score, and this importance score is what we call the SHAP value. Okay, so this is how we can classify the different structures in terms of importance to make these predictions. Now, a little bit about the method. In fact, what this does is to create a linear model G, which you can see here. This linear model, it represents the error between the neural network and the ground truth. So it's a linear model of the error. This linear model is made up of a bunch of structures present in the flow. So this Q1, Q2, Qn, this is a binary variable which takes the value of 1 if the structure is present or 0 if the structure is absent. And this phi, these are the SHAP values. These are the weighting factors which allow me to do a linear superposition of all the structures to create the linear model for the error. Now, what happens now is that we can calculate those phi values using least square regression. So as you can see at the bottom, what we do is that we have this f hat, which is the real error between the neural network and the ground truth. And I want to minimize the difference with respect to G, which is the linear model of that error, which basically through least squares allows me to find the values of phi 1, phi 2, and phi n. This is done in a game theoretic way, where this kernel pi is essentially deciding the coalitions containing structures to make this assessment of the SHAP values. Now, two main assumptions that we are doing here. The first one is the fact that the model G is linear. So we are using a linear model to represent the error. Is this fair in a turbulent flow, which is chaotic, nonlinear, highly complex? And the reality is that this linear model is actually pretty good. If you calculate the difference between the real error and the linear model of the error, that's a discrepancy of about 10 to the minus 7 for a quantity of order 1. And the reality is that there are so many structures on the order of 150 per field, and we have thousands of fields, that the linear superposition of all those structures is enough to create a pretty good representation of the error. So the linear model is okay to represent the error. And the second point, which perhaps is even more critical, is the fact that we're using an approach where we're removing structures one by one to represent the error in a system that is highly nonlinear and chaotic. The reality is that they're not exactly removed one by one. They are removed in what we call coalitions. So a coalition is a group of structures where our target structure is present. So we remove it in that context, but then we consider a different coalition, and then we remove it in that different coalition. And each of these structures is evaluated in many different contexts, such that we can see their contribution to the error, close to the wall, farther away from the wall, in a way that we can mimic the interscale mechanisms present in turbulence. So results are very robust in terms of the number of coalitions per to assess the error, the number of structures per coalition, such that we can have a pretty good representation of our error. Keep in mind that if I wanted to assess all the possible combinations, I would have 150 structures per field times about 10,000 fields, and the number of coalitions is the factorial, right? So this very quickly becomes an impractical number. But what we can do with this method is to restrict the number of coalitions to a sample that is representative of the error levels, which pretty much is what we see, that things get converged with a reasonable number of parameters to get that representation of the error. So we have a good way to get our estimation of the error levels here. Now, I will show a couple of sample results from the 2024 paper, and then I want to talk about an extension that we have done on this to more recent results. So here I'm going to show you the importance of the different structures as a function of their volume. This is a joint PDF where in the vertical axis, I'm showing you the importance of the structure divided by the volume. In the horizontal axis, I'm showing you the Reynolds shear stress of the structure divided by the volume. And the four colors represent the four quadrants of the Q events. The most important structures from the classical point of view are the ejections. This is the Q2, combined with sweeps, which are actually Q4. In this figure, it would be the blue and yellow regions. But to me, what is very interesting in this figure is the fact that if you look at this B region over here, these are the structures with the highest Reynolds shear stress. And remember, we are looking at Q events, so we are looking at the structures with high Reynolds shear stress. And in this C region over here, these are the structures with the highest importance. So what this shows is that the structures with the highest importance are not the ones with the highest Reynolds shear stress, which is a very powerful conclusion, because this means that when you define our elements, our coherent motions in terms of importance, rather than what we think should be contributing to the flow, like the Reynolds shear stress, then you can get pretty meaningful conclusions. So once again, this shows us that the most important Q events are not the ones with the highest Reynolds shear stress, which is a very meaningful conclusion when you are able to identify things purely based on importance. Okay, this was a very good conclusion that we had. We also applied this to an experimental data set, because I mentioned at the beginning that one of the motivations of this work is to apply it to experiments. And to do this, we worked with Ivan Marusik's group in Melbourne. We looked at their towing tank experiment. This is a very cool experiment where you have a plate and then you set the plate in motion such that the boundary layer grows in time, not really in space, but in time, you know, as the perturbation, the vorticity perturbation introduced by the motion propagates downwards, that grows the boundary layer in time. And this is a set of PIV measurements, which is time resolved at a Reynolds number, friction Reynolds number of over 1,000, which is an order of magnitude higher than the results before. Now, why do I want to do it in experiments? This is for two reasons. The first one is the fact that the most important structures that I identify in my flow, they're identified in a DNS, in a nicely resolved DNS setting, but I might not be able to find those structures in a high Reynolds number setting, right? Because experiment is done at a higher Reynolds number. But second, even if I could do a DNS at the same Reynolds number as the experiment, I'm not going to be able to see in a 2D PIV plane with lower resolution, with some noise, the level of detail that I'm going to achieve in the DNS. So the point is not what are the most important structures in the flow. The point is, from whatever I can measure, what is the most important stuff? Because what I can measure is what I can control, if you think about it, right? I mean, at the end, we always want to deploy these things experimentally, right? This is the real validation of these computational methods, if it actually works experimentally. So the question is not what is the most important structure in the flow. The question is, from whatever I can measure, what is the most important? And this is what we did. We applied a variant of the SHAP method. This is what we call the Gradient SHAP. The Gradient SHAP was developed by Erion and others in Nature Machine Intelligence 4 years ago now. And the Gradient SHAP, which is much more computationally efficient, what we find is an importance score for each of the channels. So basically, here we have two channels, the U and V fluctuations. We get the norm of the importance, and we apply percolation analysis in the same way as we did with the Reynolds shear stress. So you can see here the RMS of the importance, and this H is basically a percolation hyperbolic hole threshold. So in a nutshell, what we do is that we look at the regions of importance which have high importance compared with the background importance of the field, basically. So the regions that are really important. If a certain region, like Y plus 15, has an underlying high average importance, then it will be more difficult to become a SHAP structure because you really need to have a very high level of importance compared to the average value. And that's kind of like the idea. What I'm showing you here is an instantaneous flow field where in black, I'm showing you the Q events, the Reynolds stresses. In green, I'm showing you the SHAP structures. And you can see that there is some agreement. There's about 70% overlap, but there's not a full agreement. which again confirms the fact that the Q events don't tell you the whole story. Of course, it's reassuring that our SHAP extractors they have some correlation with the Q events because the Q events include strong fluctuations. So obviously they need to be important, but they don't tell the whole story. That's only understood when we look at things objectively based on importance. Okay. Feel free to ask questions or interrupt anytime, or we can take the questions at the end. That's completely up to you, but feel free to stop me. Now, this is now stuff that we are working on. This is an article that is currently under review in Nature Communications, again with Andrés Cremades and also with Sergio Ollas. So what we did was the SHAP point by point in the DNS dataset and in a larger channel so that we can have a bigger domain. So now our input is the instantaneous flow field, the instantaneous fluctuations, and we want to remove pixel by pixel data from the input to assess the importance of each of those pixels. And then what we will do is cluster the regions of highest importance and create new coherent structures completely based on importance. This is the cool part here. Here I'm showing you for one instantaneous flow field the different type of extractors. On the top left panel, I'm showing you the SHAP structures. These are the ones purely based on importance. On the top right, I'm showing you the Q events. So these are basically structures based on Reynolds-stress. On the bottom left, I'm showing you structures which are the streaks, the classical streaks. And on the bottom right, I'm showing you the vortices, the vertical motions, basically. Now, what you can see, if you just compare the instantaneous visualizations, the SHAP and the Q events share some similarities, but they have also some differences. And then the streaks and the vortices are a bit different. Now, keep in mind, historically, the streaks and the vortices are visualized. You can see them in the flow, right? I mean, since the 70s, you are seeing streaks in the flow. Since much earlier, you can see vortices. But the fact that you can see them doesn't necessarily mean that they are important. It just means that they are there. If we look at the joint PDF of the different types of extractors, so here in the big panel over here, I'm showing you in the vertical axis the y plus, so the inner scale wall normal coordinate. In the horizontal axis, the u plus, so the streamwise velocity fluctuation. And this is the joint PDF of the SHAP. On the right, I'm showing you the joint PDFs from top to bottom of the Q events, the streaks, and the vortices. Okay. Now I want to compare the probabilistic distributions of the various extractors. And as you can see, here in blue, I'm showing you the similarities with the Q events. So in this region close to the wall, we have a very good similarity with the Q events. These are basically the sweeps. Far away from the wall, you have very good agreement with this region in the Q events. These are basically ejections because they have negative streamwise velocity and they're farther from the wall. At y plus 15, now in green, I'm showing you the agreement with the streaks. You can see that we have both low speed and high speed streaks, both at y plus 15. So that's another meaningful conclusion. And if I go close to the center of the channel, there is a region of agreement with the vortices, okay, with zero velocity, but you actually have vortex clusters over here where there is some agreement with the PDF of the vortices. Something even more interesting. This is the joint PDF. This is the probabilistic distributions. But what I can also do is take the extractors, the instantaneous extractors that you can see here in one flow field, and look at the one-to-one agreement, the coincidence between different types of extractors, and then do statistics over the whole data set. So what we did was to precisely do that. So take the one-to-one agreement of the different types of extractors with respect to our SHAP. Remember, the SHAP are based purely on importance and represent as a function of the wall normal distance the agreement. So the vertical axis here is the agreement between the SHAP and the other extractors, and the horizontal axis is y plus. That's the inner scale coordinate. Some cool conclusions. In blue here, I'm showing you the agreement between SHAP and streaks. And you can see that that agreement is over 90% at y plus 15, but then it goes to 0 at the wall and in the center of the channel. In purple, I'm showing you the agreement between SHAP and the Q events, so basically the Reynolds stresses. You can see that close to the wall, we have between 60 and 70%. These are basically the sweeps. And far away from the wall, We also have an agreement between 60–70%. These are basically the ejections. And at the center channel of the channel, there is about 25% agreement between the vortices and the SHAP structure. So the vortices, which you can see in the flow, they don't have so much importance in there. I mean, there is some agreement, but not so much. What this tells us is that the classically studied structures, they only paint a partial picture of wall-bounded turbulence. So the streaks are important, but only at y+15. The ejections are important, but only far from the wall. The sweeps are important, but only close to the wall. And none of them put together represents 100% of the SHAP. Okay, so if we put together all the classical perspectives of turbulence, one can get a pretty good picture, but not a complete picture. Now, the remaining content of information is what is contained in our SHAP-based structures, which at the end is a way to measure causality. We're actually measuring causality here. Okay. I also wanted to show a couple of additional examples on the usage of explainable deep learning and SHAP for understanding causality and other mechanisms in fluid mechanics. Again, this can be applicable to basically nonlinear chaotic systems, but I want to exemplify it with turbulence. This is work, by the way, by Marcial Sanchez Agudo, who is a PhD student in my group, and Adrián Lozano Duran, who is in Caltech. So what we do is that we create an autoencoder so we can encode in a latent space relevant physical phenomena in a bunch of latent variables. Okay, so we have our flow field, the flow around an obstacle, we have an autoencoder, and here in the latent space we have a bunch of latent variables, which I denote here as LJ and LI. So in that latent space, now I have time series, which means that I can apply information theory. I mean, most of the information theory frameworks cannot be applied for the whole flow field, but now I can apply it in the latent variables. Now, if I identify a causal relation between two latent variables, between those two vectors, basically between those two time series, what I want to do is not to identify it in the latent space. What I want to see is what physical quantities are most relevant to that causal connection that I have identified. What I can do, if I find a causal connection between variable A1 to variable A2, what I can do is, using SHAP, point by point, identify, as you can see here, what are the structures most informative to encode latent variable number 1, what are the structures most informative to encode latent variable number 2, do percolation, and then what I can do is translate the causal link that I identified in the latent space into the physical one. So I can, if I really see in the latent space that there's a very strong causal link between variable 1 and 2, what I can do when I translate that into physical space is that this type of structure in the wake is very significantly linked through causal inference to these structures over here. Okay, and that's important because if I want to do flow control, I'm going to be controlling physical quantities. I'm not going to be controlling latent vectors. I'm going to be controlling physical structures. So this way of this is a way to be able to exploit the power of the whole information theory framework while preserving the connection with the physical quantities in our fluid flow, basically. Okay. And there are other questions that we are currently investigating using SHAP and explainable deep learning. For example, what are the most informative structures to predict the skin friction? This has implications for medical devices. I'm also looking at the structures most important for the different direct and inverse cascade mechanisms. What are the most informative structures to predict separation or to predict temperature fields? If I have a multi-phase flow, what are the most informative structures to predict bubble distributions or particle distributions? We're also using SHAP together with diffusion models to do optimal sensor placement. So this is something that we have developed with Abhijit Biswas-Rao, who, by the way, is going to start in Michigan also in the fall. So he will continue his PhD there. And what he's doing is, and this is something in collaboration with several groups and also with Beverly McKeon in Stanford. So the idea that we did was to use diffusion models as a surrogate for reconstruction and using SHAP to identify the regions of the domain that are most important to do that reconstruction. So to do optimal sensor placement, to really select the subsets of my input mask to make the reconstruction. So this is just a little menu of possible ideas to develop with SHAP. We're working on many of these things, and we believe that this is giving us a pretty robust, pretty strong way to assess turbulence phenomena in an objective manner, basically. Okay. So this is the first part about understanding turbulence with explainable deep learning. And in the second part, I'm going to be talking about deep reinforcement learning for flow control. And you're going to see how at the end, the two parts are going to connect. And I'm sure many of you are familiar with reinforcement learning. I will just give a little quick recap. In reinforcement learning, we have an agent, which would be our neural network. That agent is interacting with an environment, and that environment is our fluid flow. That can be a simulation or an experiment through actions, right? And those actions, in our case, is the flow control. And we like active flow control, where we have jets at the wall and we do blowing or suction, basically. Those actions are going to change the state of the system, and the state is any measurement that we have access to, and they're going to change the reward. And the reward is a measure of the quality of those actions under a certain norm. So that norm can be drag reduction, it can be separation reduction, whatever we're interested in. The idea of reinforcement learning is to iteratively try different relationships, state action, such that the reward is maximized. And that means that we want to optimize the policy pie, right? So the policy pie, given the state of the system, it will tell me which actions to take to maximize the reward. Okay. And we're going to apply reinforcement learning for flow control in a turbulent open channel. This is at a low Reynolds number, at eta 180. We're going to consider a minimal channel first, and then we're going to consider a full channel. Okay? In the minimal channel, the physics is simplified. This is work that was led by Luca Bastoni a couple of years ago, who was a PhD student in my group. And he really did fantastic work in being able to implement the reinforcement learning with a CFD solver, because we're doing a DNS here. And we want to compare with a measure of classical control, which would be opposition control. So opposition control developed by Choi, Boyne, and Kim. Well, this is now 30 years ago, right, from this paper. And opposition control has a very simple but very powerful idea. The idea is that you have your wall where you're going to actuate. You're going to measure the flow at a certain plane, which typically is y plus 15, so a sensing plane. And in the sensing plane, you're going to measure the vertical fluctuations. So you're going to impose at the wall the opposite fluctuation. So when you have flow going up, you're going to impose suction. When you have flow going down, you're going to do blowing. And this simple idea, it works actually pretty well, especially at low Reynolds numbers. Then at high Reynolds numbers, the performance starts to degrade. But this is going to be our baseline to see if reinforcement learning is going to allow us to discover something a bit more nuanced, something a little bit more sophisticated, right? And this is the framework that we're using. This is a multi-agent reinforcement learning framework, MARL. This was described in this article in Nature Reviews Physics, also with Steve Branton and Beverly McKeon. Essentially what we do is that we sense the flow at y plus 15. So we measure the stringwise and wall normal fluctuations there. At the wall, we have these blue regions that you can see here. These are called pseudo environments, and I'll tell you more about it in just a second. And the reward is going to be the drag reduction. So what are the pseudo environments? We want to, in MARL, what we want to do is exploit the invariances in our flow. So the flow is going to be periodic in the stringwise direction and the spanwise direction. This is a channel. Periodic, meaning that the flow is statistically homogeneous in those two directions, which means that I can effectively parallelize the DRL training in all these directions using all these pseudo environments. So in all these pseudo environments, I have the same agent, it's a copy of the same agent, which is basically trained in parallel in all these places, because again, the instantaneous flow field is different, but the statistical properties are the same. And not only I can accelerate the training and speed up the training, what I can also do is let the agents cooperate, because my reward for each of those pseudo environments is going to be at the wall, including some overlap with the neighboring pseudo environments. So with multi-agent reinforcement learning, what I want to do eventually is decide the action, which is the velocity at the wall, either blowing or suction. And those agents are going to cooperate to achieve the maximum possible reward overall. That's the idea. So this way of cooperative learning and scaling up and parallelizing the learning, in our experience, this is basically the only way, well, or let's say a quite efficient way to overcome the curse of dimensionality of reinforcement learning, especially in the context of turbulence, right? Because in turbulence, the dimensionality grows very quickly. You have very high Reynolds number, chaotic motions. I'm going to show you an example at high Reynolds number later on. And then this way really allows us to be able to speed up the training and get pretty good reconstruction and pretty good performance in the control. Okay. Now, let's look at some results. In the minimal channel, in blue, I'm showing you and this is for one episode, but of course, these are statistics average over thousands of episodes. In blue, I'm showing you the drag reduction as a function of time from the reinforcement learning, and in orange, from the opposition control. From opposition control, we get 26% drag reduction. I told you that at these Reynolds numbers, this method works pretty well. With reinforcement learning, 43% drag reduction. So we can significantly outperform the drag reduction in the opposition control. If we take the policy, learn in the minimal channel, and I deploy it in the full channel, the Reynolds number is the same, but not only you have a bigger domain, the physics is more complex because in a minimal channel you constrain the number of streaks, right? Whereas in the full channel you have the complete near wall cycle, the complete near wall dynamics. But even in this case, the reinforcement learning still outperforms the opposition control. So here, opposition control gives me 20% drag reduction, whereas the deep reinforcement learning gives me 30% drag reduction, which is very promising. Now, at the end of the day, the reinforcement learning can find a much more sophisticated control strategy to be able to affect the flow. Here, I'm showing you a quadrant analysis. So this is at the end is a joint PDF, a joint probability density function, where the horizontal axis is the streamwise fluctuation at y plus 15. The vertical axis is the wall normal fluctuation at y plus 15. And the color indicates the density of probability, whereas in the first row, you have the uncontrolled flow. So what you typically have in healthy turbulence, in standard turbulence, is a predominance of the Q2 and Q4 events. So that would be the top left quadrant and the bottom right quadrant. And this is consistent with what we saw using SHAP. The Q2s are the ejections, and the Q4s are actually the sweeps. In the second panel, I'm showing you the joint PDF doing opposition control. And when you do opposition control, what you can see is that the range of fluctuations shrinks, but the flow is basically very similar. I mean, you still have a predominance of the Q2s, which are the top left, and the Q4s, which are the bottom right. However, in the last panel, I'm showing you the deep reinforcement learning. What you can see is that the predominance of the Q2 and Q4 events is gone. Now we have a pretty even distribution across the 4 quadrants in such a way that the flow gets significantly modified by the reinforcement learning. If we visualize the control, what we see at the top, this is the velocity at the wall. This is the opposition control. So the opposition control progressively over time, as the flow gets controlled, the actuation becomes smaller. And in the DRL, which is the second panel, what we see is a sort of two-step control, like a bang-bang control. This is actually very common in reinforcement learning to identify a bang-bang control structure. This is in robotics, in drones, UAVs, this is actually quite common. And what this does effectively, in this particular case, in not all the cases we find a bang-bang control, but in this particular case, what we are doing is effectively stabilize the streaks. So you can see that the flow is still turbulent. There are still turbulent extractors and turbulent fluctuations, but the streaks get completely straightened. So the instabilities and spanwise meandering is completely cancelled by the bang-bang actuation that the flow is actually imposing on it. And these are very recent results by Miguel Benitez, who is a postdoc in my group. this is something that I'm very excited about. So what I'm showing you here on the left is the drag reduction as a function of time, same figure as before. In blue, I'm showing you the opposition control, so same as before, and this is in an open channel. So if we look at the orange line is the drag reduction when my reward of the reinforcement learning is to minimize the wall shear stress. Okay, and you can see that there is a bit of this sort of bang control is kind of observed here, right? And it outperforms the drag reduction of the opposition control. Then in purple over here, I'm showing you the results when the reward of reinforcement learning is to minimize the presence of streaks in the flow. Okay, so the reinforcement learning is not trying to reduce the drag, it's trying to minimize the streaks. In green, I'm showing you the drag reduction when the reinforcement learning is trying to minimize the Q events, so the Reynolds stresses. And you can see that the performance is also quite similar. Now here in black, what I'm showing you is the drag reduction when the reward is to minimize the SHAP structures. So we have the flow field, we identify using explainability the most important structures in the flow, and our reward is not reduce the drag. Our reward is reduce these guys, because these guys are the ones who are creating the turbulent fluctuations. These are the most important structures in the flow. And look at what happens. Drag reduction is similar to the DRL approaches, but at some point it just skyrockets. And you can really see a drastic increase in drag reduction. Many of the trajectories, this is of course the average over many trajectories, many of the trajectories become relaminarized. And if you look at the power input, which I'm showing you here on the right, from time t plus 1200, the power input is basically zero. So not only we get higher drag reduction than with any other method, we also get minimal power input. This is a very, very efficient control, which kind of makes sense. I mean, this is essentially causality-driven flow control. I identify what is the most important structure in the flow, I attack it, and I get an optimal way to control it. So I'm very excited about that. And we have also shown the applicability of these methods in many, so not only in turbulent channel. You can see here in the top left an article that we just published in Nature Communications, where all the data and all the codes are available online. So if you want to do reinforcement learning, you can download it and play with it. This is for a turbulence separation bubble. So we basically reduce separation much more than with classical periodic control. So, and this is a Reynolds tau of 750. So this Reynolds number is actually quite high. Multi-agent reinforcement learning significantly outperforms the classical periodic control. Here I'm showing you the control in 3D cylinders. This is a work by Paul Suarez, who is also in my group. And here this is quite cool because we start with, these are 3D cylinders, but we start with a Reynolds number of 100, where the flow is two-dimensional, and we increase the Reynolds number up to 400 and beyond. And what you can see is that when the flow is two-dimensional, the actuators across the cylinder all do the same. So they learn to do a two-dimensional control. And as the span-wise instabilities emerge in the wake, the reinforcement learning learns to create controls that exploit the span-wise instabilities in the wake. In the third example that I'm showing you at the bottom, this is work by Joel Bassant. We look at 3D relaminar convection, where we want to minimize the convective heat transfer. So we want to minimize the Nusselt number. And what we can see here on the lower wall is that we have, these are the original convection cells. With reinforcement learning, we create a scenario where the convection cells get completely aligned in a much more stable regime. So we effectively change the topology of the flow to obtain more efficient heat transfer configurations. A couple of additional points on the usage of reinforcement learning. We are also working on using reinforcement learning as a modeling tool. So basically as a Savary scale model or even as a wall model or both. And the idea here is to use reinforcement learning to basically create a forcing, which is the Savary scale stress, where the reward is a spectrum. So we want to have the right spectrum for our flow, basically. And we're also working on ideas combining foundation models and reinforcement learning to have a pretty good surrogate to speed up the training. So if we can come up with a good way to develop a good surrogate model, then we can do most of the training with a cheaper surrogate, and then do transfer learning to more detailed and much more expensive simulations just to do the final tuning of the model. Okay, so these are two ideas that we're exploring, both pretty promising, just to show you that reinforcement learning can be used for more things in the context of turbulence beyond just flow control. So as a summary of what I've been talking about today, we're using DNS, we're producing high quality data for aeronautical flows. SHAP and explainability allow us to identify what are the most important structures in the flow and to identify essential causal links in our turbulent flow. In the third part, I've also talked about reinforcement learning. Reinforcement learning is significantly outperforming classical control methods, in particular when I combine reinforcement learning with explainability to target the SHAP structures, to target these most important structures in the field. All the codes and all the data are available online. So use this QR code that you can see here, and then you can access the repository of my group, the Vinuesa Lab. Everything is there. And I have more information about these papers in my YouTube channel. So if you go there, you will see videos about all our papers. So all the details are there. And also feel free to reach me in social media. My email is also here at the bottom. And I also have a Michigan email, so you can also reach me there. And yeah, I mean, this is all I have for today. I made sure to leave enough time to discuss questions. So yeah, happy to take your questions and comments.
That was a really interesting talk. Thank you.
Thank you so much.
So with that, we'll open the floor to some questions. So if there are any questions in the room or online, people can unmute themselves or just type in the chat as well. So I have a question. So you identified the most important regions by masking somewhat the flow field as input to the unit, right? So and you were matching that with the true field as well. So since you were doing some sort of a time series prediction, did you check for long time horizons? Did it make any difference? Because some features identified early on as not relevant might be a bit more relevant later on.
I'm not very interested in the prediction, the forecasting in time. I'm just predicting a future state of the flow. And that future state of the flow, we have tried with separations between input and output between 1 to 10 viscous times, which are characteristics of the near wall dynamics. And the results are very consistent over that range. We basically get the same from 1 to 10 viscous times. The reason for this, when you do causality analysis, is that you need to create a lag. You need to look at what is the time horizon over which the removal of the input information is going to affect your output, right? So this is motivated by causality. In that time horizon, not only the result of the explainability is the same, but the prediction of our unit is the same. I mean, we never go above 1.5% error, which is in principle accurate enough to make my predictions. If I wanted to have longer time horizons, so let's say now that I want to have a characteristic time of the outer region, then a different model would be required, right? But for this control, because I'm doing near wall control, the type of important structures that I want to look at are the ones with characteristic times of few viscous units. So in principle, the choice of that lag is motivated by the control that I want to do later on.
So if you extend this, I think you were using these important regions for your reinforcement learning algorithm, right? So, and you mentioned that the same regions weren't being identified when you changed the Reynolds number. So for your reinforcement learning algorithm, did you have to re-obtain those important regions again, or when you changed the Reynolds number, or did you just stay with one Reynolds number throughout?
Yeah, that's a very good question. I mean, the results with the SHAP and the reinforcement learning are very new. I mean, this is really ongoing. But so to give you an idea here, we are just calculating the SHAP values for the uncontrolled case. But of course, as you control the flow, the most important things change. And as you increase the Reynolds number, the most important things change. Still, these results are without readapting, without retraining to the new conditions of the flow. So in a way, this is using kind of a bit outdated information of what is important and what is not, and it still outperforms the other control methods. Now we're currently working on dynamically adjusting the SHAP and the reinforcement learning. You see, so as I control the flow and the flow becomes different, it goes in a different trajectory, we adapt what is the most important stuff along this trajectory, and the same with the higher Reynolds number. Although I should say that comparing our numerical results below Arita 1000 with experimental ones beyond Arita 1000, the characteristics of the most important extractors are actually pretty similar. The PDFs are very similar. But this is an area of investigation. I mean, if we go to Arita or 10,000 or 20,000, then we will have to do this a bit more carefully. But for now, it's actually, yeah, working pretty well, and we are planning on incorporating this dynamic adaptation of the SHAP.
Thank you. That's any other questions?
I have two questions. So for the first question, it's related to slide 21, where you were showing the coincidences between the SHAP structures and all of the other flow features. So what I was wondering is that the SHAP method is an approximation, right? So any structures it identifies, I don't think it's guaranteed that that covers all of the important structures that exist. So would it be possible to repeat this sort of plot, but do a comparison of two different SHAP methods so that potentially you could identify even more important structures and account for all of them in the subsequent reinforcement learning?
Well, I mean, we have re-evaluated the SHAP several times with different coalitions and different combinations, and the results are the same. I mean, so we find the same regions of importance, basically. Because maybe you're going, I mean, the unit, I mean, I have my input, I have my output, that's it. If I have a probabilistic method, like a diffusion model, then things are more complicated. And then, for example, for the optimal sensor placement, where we combine the SHAP and the diffusion model, the probabilistic aspect to it makes it that you need to reevaluate few times, so you actually get all the possible combinations. In that case, you're right, if the model is probabilistic, and that's what we have done for the optimal sensor placement case. But in this case, there's no probabilistic aspect, right? You have your input, and the unit evaluates and gives you your output, basically.
Okay, that makes sense.
But it's a good point, actually.
Yeah. Okay. And then I had just one more question, which is a little more stupid. So for the multi-agent reinforcement learning, I was curious as to how you define the reward function. So is it something that's common for all of the agents, or every agent has its own reward function related to randomization? Or
I mentioned it a bit briefly. In this example, when the reward is the wall shear stress, because you saw later on that I use the SHAP and other possibilities for the reward, but when the reward is the wall shear stress reduction, what I have is, maybe I can draw, yeah. So if I'm looking at this pseudo environment over here, the reward is defined for a region overlapping with the neighboring pseudo environments, so something like this.
okay.
So the drag reduction in a region, something like this. Why? Because I want to have local information for that pseudo environment, but also I want to see how the overlap with other pseudo environments allows them to cooperate, right? Because the parameters of the MLP, at the end it's an MLP, in all those pseudo environments are the same. So they are all seeing the different parts of the reward, but with overlaps. So they can actually work together. So the cooperative aspect comes with that overlap of the region where the reward is defined.
Okay. And then how many agents do you need to set up so that the state space also becomes tractable for every individual agent, for at least this example?
Yeah, the limitation here is computational, of course, right? In this particular, when we do the minimal channel, this is a pretty reasonable depiction. These were 16. So in the minimal channel, each pseudo environment has basically one grid point, and that grid point is an actuator, right? Blowing or suction. When we go to the full channel, then one needs to put several grid points, several actuators in the same pseudo environment. And in the pseudo environment, there is only one action coming, so all of them are doing the same. basically.
Okay.
So in the full channel, we may be talking about 2 by 2 or 3 by 3 in each of those sub regions, basically. So you lose a bit of granularity in your possibility to actuate, but it's actually not really needed. I mean, the size of the scales that you have, if you think about it, the span-wise spacing in a DNS is about 5 viscous units, right? And the span-wise spacing of the streaks is 100 viscous units. So even if you have 3-4 grid points for one actuator, what you want to have is at least 2 or 3 different actions within one wavelength. So let's imagine you have one wavelength. You want to be able to have something. Let's imagine something like this. So in that wavelength, you can do 3 different things. Right? So that allows you to have enough control authority to do something to that wave. And then in the full channel, if I have 3-4 actuators doing the same, like this, that means that even if I'm putting several grid points together, I still have enough level of detail to be able to act with enough actuators per wavelength. So I have enough control authority, basically.
Yeah, thank you. That really makes sense. Yeah.
Very good questions.
Right. Are there like any other questions? I guess I can ask one more. You briefly mentioned the use of these methods for some sort of inverse design or experimental design tasks, right? So basically adapting these locations or most important locations, do you have any thoughts on the computational overhead? Because if you adapt them at each time step or after every 10 time steps or something, what's the typical computational overhead of just randomly selecting some sensors versus doing based on such an approach?
So are you asking about the optimal sensor placement problem?
Yes. Yeah.
So let me go there. That was the slide at the end of the SHAP. So, oops, sorry. You're asking about this one, right?
Yes.
Yeah. That's a good question, but for this particular problem, the motivation is an urban environment. So you have a city where you want to measure in different locations, and from those measurements you want to reconstruct the flow field. Our approach here is that the sensor locations are fixed.
Oh.
So we don't want to move the sensors. There's other possibilities, other approaches where you could have drones and dynamically change the drone locations to optimally sense the flow, but we are not doing that. That's something that we are doing in another project, but I'm not talking about it here. Here I'm talking about static sensors. So for each snapshot, I would get distribution of the SHAP for each snapshot. What I'm showing you here is the average over the whole, is the time average over the whole data set, basically. So these are statistically the locations that are optimal to reconstruct the flow. And of course, as the vortices are going forward in the wake, in some cases, this distribution is not going to be optimal, but statistically, this is going to be the most optimal. So yes, this has a computational overhead. That's why we want to do it only once and leave the sensors fixed.
But if you use this sort of an approach for a problem, they want to adapt this, do you have any thoughts on the computational overhead of this approach?
Yeah, so for the problem where we want to adapt them, with the drones, for example, then we probably would not use SHAP, because SHAP is quite expensive, relatively speaking, in terms of the number of evaluations that you need to do. This relies on a diffusion model, and the diffusion model is also not cheap. I mean, the evaluation of the model is cheap. One of the important aspects here is to set the number of diffusion steps and the number of batches that you can afford to use to keep a pretty good reconstruction, basically. So that's one control parameter that is important. And then we are exploring generative, probably with graph generative networks. So that's something that probably when we are doing it dynamically, it's going to be more efficient than SHAP. And that's still in a kind of like an exploratory stage. So to kind of summarize the answer, I would say that one key, I would not use SHAP if you want to do it dynamically. I would really control the number of steps and the number of batches in your diffusion model, so it's a cheap way to evaluate it. And yeah, and we're looking at different methods. Reinforcement learning is another clear candidate to be able to dynamically adjust the number of candidates of the location of the sensors dynamically. But that's still ongoing.
Thank you.
That's a good question too.
Like, are there like any other questions? People online? Okay. So if not, let's just thank the speaker once again.
Yeah, thank you so much. It was a real pleasure to present, and a real pleasure to answer your questions. These were very interesting questions.
It was very insightful. Thank you for taking the time to present your work.
Thank you so much. And feel free to reach, I mean, all the codes are available online. So if you want to try something, just feel free to contact and yeah.
Yeah, and we encourage all the participants to like reach out or like if they have any other questions and stuff. Yeah, with that, thank you, Professor, and we look forward to see you at the university. So.
Looking forward in a few months. I'll see you there.
Yes.
Take care.
Okay.
Have a good day.
You too. Thank you.